students, today we will discuss about the NMR spectroscopy. So, NMR spectroscopy is nothing but nuclear magnetic resonance spectroscopy. So, magnetism, we all know that whenever in a moving charged particle, if it is going to be there, so it creates a magnetism around it, which we call it as electromagnetism. So, now this is going to happen when this particular particle due to its charge and the motion. So, this magnetism mainly it is going to get generated because of the spin of that particular charged particle. So, in a chemical molecule, so we will be having number of atoms which are bonded to each other in order to form a molecule. So, they will have negatively charged electrons and positively charged nuclei, that is the protons within the nucleus. So, due to this particular negatively charged electron which is spinning around its axis as well as spinning around the nucleus, they will have their own magnetic power and they are going to generate a magnetism. At the same time, nucleus also having a proton and which is spinning on its own axis is also going to be generating the tiny magnetism around it. So, due to this, we can say that whenever in electron bonding, means whenever in chemical bond we say, it is going to get formed by the sharing of electrons. That means there will be two electrons in a chemical bond, so which is going to be generally have an opposite spin. So, this presence of two electrons simultaneously having an opposite spin creates a diamagnetism, because the spin, as it is going to be opposite, the magnetic property is also going to be opposite and it will cancel each other. Whereas, if there is only one electron or only one odd number of charged particle, if it is going to be left over, it creates paramagnetism. That means the molecule or the atom now behaves like a magnet. So, further the property of an atom, which is going to be quantized based on its magnetic spin. So, nuclear magnetic resonance spectroscopy mainly takes advantage of this particular fact that an atom and as a whole the molecule can act as a tiny magnet, provided it is going to have an extra electron or an extra proton. So, since we in nuclear magnetic resonance spectroscopy we talk about nuclear magnetism, so we will mainly discuss about the magnetic property which is mainly because of the nucleus, that is due to the charged proton particle. So, if we take an example of to explain this better, we take an example of H1 NMR or H1 as an example. H1 has a nucleus which is having only one positive charge, and it is, we can say it is a spinning nucleus itself. So, this spinning nucleus generates a tiny magnetic field around it, we call it and will have a magnetic momentum, that magnetic spin moment we denote as mu. And when against to this particular tiny magnet, if we are going to keep an external magnetic field, for example, whenever we hold a bar magnet, so on the means with in our hand, it always try to align itself into north and south pole, oppositely as south and north, means opposite poles wise it is going to align itself. So, how much ever you rotate, it will come back and it will align like itself, means same way. In the same way, this tiny magnet which is going to get generated due to the spinning of protons, so will have its own magnetic momentum as well as magnetic direction. Now, against to this particular tiny electromagnet, if we are going to keep another external magnetic field, if it is going to be applied by holding two magnets having a little more magnetic field strength, then what will happen is that this particular tiny magnet, the proton will try to align its magnetic direction such a way that against the applied external magnetic field, means opposite to that against magnetic field, so that it can maintain either parallel or anti-parallel means alignment. It can show based on the strength of the applied magnetic field. So, now this alignment or orientation refers to as spin states of that particular magnet, we can say, like it can have minus half or plus half spin. Now, the magnetic spin moment wobbles or processes around the axis of the external magnetic field by an angle theta. Now, this orientation between the magnetic field of the tiny magnet and the against the applied external magnetic field is going to happen at an angle called theta, and it rotates around its axis, okay, with a particular frequency of omega, and this frequency of omega with which the tiny magnet is going to spin around in presence of external magnetic field, we call it as Lamarr frequency. You can see here how this particular B naught is the external magnetic field, and the circle is the tiny magnet, that is the nucleus, and the mu you can see that is the magnetic momentum, which is going to have its own direction with respect to the applied external magnetic field. Now, let us take an example wherein if we are going to provide little amount of energy to this spinning nucleus, when it absorbs some amount of energy, then automatically this spinning nucleus, now its spin, the rotation will get altered, and magnetic field strength will also get, or magnetic momentum will also get increased. So, this increase in the magnetic field momentum can alter the direction of the magnetic field strength. Now, due to absorption of energy, this nucleus will orient in another direction, or you can say opposite to the earlier direction partially. That means, this changes the theta of the angle between the applied and external applied and the tiny magnetic field strength. So, you can go to this particular YouTube link, which will help you in understanding better, as there is simulations available which will explain you, means it may help you in understanding this particular concept little more better. Now, as I told you, so at lower energy, when it is not excited, it is going to have a plus half spin, and it will have an energy content E is equal to minus mu naught mu dot B naught sin theta. That means, mu is the magnetic moment, B naught is applied magnetic field strength, and sin theta is the angle, theta is the angle. And when that high spin state is going to obtained by the absorption of energy, then the spin becomes plus half, and magnetic momentum now becomes, instead of minus mu, it becomes mu B naught sin theta. Now, if we are going to calculate the energy difference, that is delta G, the energy change, then it gives delta E is equal to 2 mu B naught sin theta. So, there is the energy difference between the two states when it is having plus F and minus of magnetism. You can see in this particular, say, like energy is going to get increased from minus of, spin becomes plus half, and magnetic field strength is going to get altered. So, this change in the delta E, it varies in a manner which is directly proportional to the applied magnetic field strength. The applied magnetic field strength, that is the B naught. So, which we can actually convert it into E is equal to h nu formula. If we apply, then we can deduce this particular equation into nu is equal to, that is frequency is equal to 2 mu B naught sin theta divided by h, where h is a Planck's constant, that is nu is equal to E by h. So, where E value we are going to put it here. So, that means frequency is going to guide the change in frequency can be used as a criteria in order to vary the energy content of the tiny magnet. Now, in the NMR spectroscopy, so here depends upon the absorption of electromagnetic radiation, that is from the radio wave part of the spectrum, causing the nucleus to undergo transition from low energy to high energy states, because this energy content will be sufficient enough to bring about the change in that particular magnetic spin, the spin of that particular tiny magnet. So, the precise value of nu required for this particular transition depends upon the identity of the nucleus, means what is that particular nucleus, for example, whether it is hydrogen or whether it is carbon or nitrogen or phosphorus. So, that way, so what is that particular nucleus and precise chemical environment, whether that particular nitrogen, for example, whether it is in the form of NH2 or NH3, is it in the amino acid structure or is it in amine structure, and how many number of other atoms are linked, and how that nitrogen is linked with all the other atoms. So, all these environmental aspects also going to affect the frequency of energy, means the radiation which is going to get absorbed by the nucleus. Now, in order to undergo an NMR transition at a particular value of nu, the frequency, a specific set of circumstances called the resonance conditions need to be exist. So, only when the resonance conditions are existing, then the absorption of radiation will take place and resonance will happen. Now, what is this resonance condition? This condition can be achieved when the frequency of rotation of field represented by B1, that is the tiny magnet field strength, equals to the Lamarr frequency. That means, when the magnetic field strength of that particular, or the spinning, whatever the spinning of that particular tiny magnet is there, that particular spinning frequency, when it is going to, the angular frequency, the omega, when that is going to become equal to the Lamarr frequency, okay. So, then that particular tiny magnet can absorb the radiation and undergo resonance condition. What is this resonance? Resonance is nothing but it is the, what you call it as orientation and disorientation of that particular tiny magnet, because the tiny magnet, when the energy is applied and taken away, so it goes up and down, or in other words, magnetic field strength direction becomes continuously get altered. So, this alteration in the magnetic field strength direction with respect to the applied magnetic field itself is having a frequency, that is the Lamarr frequency, and that matches with the nu of the radio frequency, then the resonance will takes place. Now, the relationship between the Lamarr frequency and the radio frequency can be calculated, can be given by omega is equal to 2 pi nu. Okay. So, when omega, that is the frequency with which the spinning tiny magnet is actually spinning around, is equal to 2 pi nu. So, then the frequency, Lamarr frequency and radio frequency is going to become equal, and then the tiny magnet is going to be said to be under resonance. You can see here. So, this is a tiny magnet B1, alignment is going to be such a way that with respect to the external magnetic field strength. So, this is the field strength of the tiny magnet, the direction of field strength, and this is the Lamarr frequency which is running in the same direction and with the same content. So, when radio frequency is applied, so it undergoes excitation or it undergoes a resonance. Now, how exactly the NMR is going to get affected by the atomic identity? Atomic identity means the sense what particular atom is that particular nucleus belongs to. So, in case of biological system, so we have protons. Proton NMR is especially very much informative, because all the biological molecules have large number of H plus or protons within them. So, it will give large amount of information regarding those particular molecules. Now, nuclei possessing even atomic mass and even atomic number will not have any kind of net spin. Net spin becomes I is equal to 0, because they will even number means the spin is going to be opposite and it will cancel each other. So, when NMR information is going to be says that, then it is says that it is isotope specific, allowing us to obtain the distinct spectra for H1, H2 and etc. So, each nucleus possessing spin, that is, let us say if it is having 0, undergo a characteristic transition from lower energy to higher energy state, okay, and undergo a resonance condition, that is delta E is equal to gamma by 2 pi into B naught. So, you can see here in this chart. So, these are the nucleus and these are the spin which is going to be possessed by those particular nucleus, and the abundance which is going to be obtained within the nature, okay, is given. And in this particular equation, delta E is equal to gamma by 2 pi into B naught, where gamma is the constant property of a nucleus and it is called as magnetogyric ratio, and it sometimes people also call as gyromagnetic ratio also. So, this gyromagnetic ratio is a very specific property of the nucleus, and by knowing that we can say which nuclei is the one which is undergoing the resonance. Now, in NMR spectroscopy we have some aspects, because when we are studying the nucleus, and we also need to know two aspects I told you first initially. One, what is the type of nucleus, identity of the nucleus. Second is chemical environment or environment in which it is. When we say environmental in which that particular magnet is present or the nucleus is existing, so there we come across with the chemical environment, that is all the different varieties of atoms which are surrounding it and which are actually bonded to it. So, for example, in case of you take a proton like CH2, whereas H is a proton, so will achieve the resonance condition at different radiation frequency to a proton which is part of a CH3 which is a part of NH2, like that. Means the CH2 proton resonance is going to happen at a different frequency than that of CH3 proton and NH2 proton. So, this is mainly because the nearby nuclei, the carbon or other hydrogens or the nitrogens, they are all different, and these nuclei undergo a means will have different proportional of effect on this resonating proton, and will show some amount of that effect we call it as shielding. So, this is known as the chemical shielding. So, the chemical shielding effect, it is going to alter the magnetic field experienced by the nucleus. Why? Because for example, see, nitrogen has its own magnetism, carbon has its own magnetism, and adjacent hydrogen will also have its own magnetism. So, the magnetic field strength of these different tiny magnets, and as well the direction of magnetic field strength of these tiny magnets are going to be different, and that ultimately is going to create an amount of magnetic field strength which can actually mask the magnetic field strength of the tiny proton. Okay. So, let us say if you take CH2, in CH2 there is one CH2, one hydrogen, you can name it as alpha, other one as beta, and a carbon. So, carbon and beta hydrogens will have different magnetic field strength and different magnetism when compared to alpha hydrogen, and the magnetism of the carbon and as well as beta hydrogen can shield the magnetic field strength or can shield the alpha hydrogen's magnetic field strength, okay, from whatever the magnetism it is supposed to feel, okay, due to the applied magnetic field. So, this is mainly because these two can shield the magnetic field strength by absorbing some amount of magnetic field strength of the applied one. So, therefore, the effective magnetic field strength is going to be B effective is equal to B naught into 1 minus sigma. What is sigma? Sigma is called as the chemical shift, and this phenomenon generally it is going to operate with a very short distance of 3 to 8 angstroms generally. Okay. And for example, in case of CH2, if you take again as an example Okay. So, CH2 in amino acid serine and CH2 in monosaccharide will have similar kind of frequency of resonance. Okay. So, that means the external environmental effect is going to be limited to very small distance. So, intermolecular shielding effect like these can be used to determine the chemical structure and as well of that particular tiny small molecules just directly by the NMR spectra. So, one more kind of shielding we may come across with called as space shielding. So, the space shielding effects are also possible, but however, between adjacent chemical group it is going to be little less, it can happen, but not within it. Okay. So, there is this is the diene paramagnetic shieldings. Then we come across with a largely sometimes what happens instrumental reasons, it is going to be difficult to calculate the frequency of resonance correctly in these particular cases. So, therefore, in order to understand it and clearly measure it, people use a standard, that is tetramethylselene. So, first usually this reference compound is going to be analyzed, and taking this reference compound's chemical shift value as 0, people are going to measure the chemical shift value of other compounds and atoms or molecules or groups. So, the frequency corresponds to the resonance conditions for each transition in a sample is then expressed as chemical shift. So, it is measured as parts per million. So, delta is equal to nu s minus nu ref divided by nu ref into 10 power minus 6. Nu res is frequency of vibration of standard, sorry, frequency of resonance of standard, frequency of resonance of reference. Okay, that will give you the delta value, that is a chemical shift value. And this chemical shift value will have affected, it can get affected by electron withdrawing group and electron donating groups. Withdrawing groups generally increases the shift, whereas donating groups or electropositive groups generally tend to decrease it. So, but and this chemical shift can have both positive and negative values. So, you can see in this particular spectrum, this is a simple spectra of ethyl alcohol which is having CH3, CH2OH. So, in ethyl alcohol altogether we can come across with 6 protons, 1 oxygen, 2 carbons. It is 6 hydrogens, 1 oxygen, 2 carbons. So, now how these 6 protons, 1 oxygen, 2 carbon are actually linked can be understood well by this particular spectrum. Okay. So, you can see that there is one single peak for hydrogen attached to oxygen, whereas there is going to be 4 peaks for CH2, 3 peaks for the CH3, and TMS is considered to be having one peak, a single peak. Now, this is going to give more information in identifying the structure of the means a molecule, because this you can see here the CH3 having 3 protons in it and CH2 having 2 protons in it. Supposedly we should expect the CH2 is having more amount of chemical environment, means it is surrounded by one side 3 protons, another side 1 proton. So, because of that it is showing quadruplets. Okay. So, one because of the CH3 effect, another for OH effect, another because of itself. So, altogether it will give a quadruplet, whereas the CH3 is going to give a triplet, that is in this 3 peaks. So, you can see these 3 peaks is mainly because it is being affected by the carbon is affecting, on the other hand CH2OH is affecting. So, it is going to give only triplets, and whereas OH it is going to give only one peak, because it is mainly affected only because the factors which can affect is only the CH3, CH2, the ethyl group itself. So, this is how this particular splitting will take place and gives an idea, and most with this particular peaks once we get it and chemical shift value when we get it. So, the only possible kind of linking will be CH3 CH2 OH. So, this is clear in the parts of the spectrum due to the CH3 and CH2 groups, or 3 and 4 peaks are visible respectively, rather than we get a single peak. So, this is how chemical shift is going to affect and plays very important role in the structural elucidation of small molecules through NMR spectroscopy. There are many other factors which further affects the nuclear magnetism, like spin-spin coupling is there. Okay. So, all these aspects we will see in the next class, and even in instrumentation and application part. So, thank you. So, go through this, it is a very important topic and very helpful.